and I have been working here from past 5 years, and I work on embedded projects. Okay, so I wanted to introduce like Apra Labs as an organization, what it does. Like in Apra Labs, we work on technological solutions where people in startups who have great ideas, but they don't have solutions for those ideas. So that's where we come in. We provide technological solutions to them, and we make them a great success. So few of our clients we have for whom we have given a successful solutions. So in Apra Labs, we are having a diversified technological areas, and we work on cutting edge technologies. So as such, I mean, we are into computer vision for embedded machines, then surveillance, medical imaging, robotics. So there we are into. Next, we work on app development for iOS and Android, as well as we work on, I mean, that is Apple TV. You guys might have heard about it. So we work on that also. So we work on full stack development also. We have a team which work on AI and ML and solve some of the solutions. I mean, they have given some of the solutions for basketball and ice hockey. So, I mean, in this basketball and ice hockey, you might have seen like people play, and there are lot of people who are generating highlights for the game. So AIML comes into picture here, and it creates an automated highlights. So it will be easier for them to just go there and check whether this highlights needs to be produced to the customers or not. I mean, clients or not. So we have wood chip classifications also. So wood chip classification is like in paper mills, you need wood chips, and they have to like manually find out which are the good wood chips, which can give you a good paper, and they have to segregate few of the bad wood chips. So there, the computer vision will come into picture, and they classify which are the bad wood chips and which are the good wood chips. So it made the things faster. Okay. So this is what we did, and also in medical field. So you guys know the RDT, rapid antigen test for COVID. You have seen those strips, right? So like COVID, I mean the strips for RAT. So there is something called RDT also for flus. So most of the people, I mean, we are very much familiar with this RDT strips, but most of the people are not so much familiar to find out like whether they are positive or they are negative for those flu or any antigen test. So we have a solution with AIML. So you can take a picture, so with a phone, and it will detect like whether you are positive or negative for the antigen test. Because whoever has a flu, they will be like shivering, shaky, and they won't be able to understand. And they have most of the time denial that they don't have the flu. So that's where we come into picture. We find out, we give the right information to them, so that they can go to the medical premises. I mean, wherever there is a clinic or anything, they can approach there and get their flu treated. Okay. So we have been working on a framework. We have been working on a framework like which is been developing from past 3 years, and we have like added our collective knowledge by we used to solve complex solutions for complex problems and give a solution for that. So we compiled everything and put it in this framework that is called Apra Pipes, and we will be covering this in next slides. Okay. Yeah, that's it.
So thank you, Omkar, for giving the intro. Now let us have the ice-breaking session. So in this session, there will be certain chits. You need to pick up the chit, give your intro, and there will be a question in that chit. So you need to answer that question. So I would like to call Shweta to give a demo.
Okay, I guess the people who are already here have already picked up a chit for themselves. I'll just pick up one for myself. Okay, so hi everyone, my name is Xilinx and I work here at Apra Labs as a software engineer. So my question is, what looks easy peasy lemon squeezy but is actually difficult lemon difficult? I just say living life. Surviving. So we can just continue.
Further, you can come.
But I had picked the
Yeah, you already have.
You-
Hi everyone, my name is Tarun. I work as software engineer at Xilinx Technologies. The question is, if you could invent a holiday, what would it be and what would you call it? Okay, really interesting. I think just a random holiday in any week when you don't feel like to work. Okay, some random name. I'll just name it random.
So you can now.
Hello all, I'm Dhrutit. I'm currently a student at PS University. My interests are machine learning. Question is, if you were coming out onto a stage, what would your entrance theme song be? I'd say Manzar Hai Naya from movie.
So now,
Okay, hi everyone. I'm Palak and I work at Apra Labs. I've been working here for a year now. I work on embedded systems. And my question is, tell us about the month you were born without specifying the actual month. I guess it's the lovers month. Yeah.
next month.
What is the best advice you have ever had? Okay. So I'm Manoj. I work here at Apra Labs as a product engineer. So my question is, what is the best advice you have ever had? The best advice I ever had was, it's from a movie called Rocky. It doesn't matter how many times you fall. It doesn't matter how many punches you take. You have to get up every time and move. That's what I've learned. Thank you.
You can.
Hi everyone, I'm Riya. I work here in Apra Labs as a software engineer. And my question is, would you rather be invisible or be able to read minds? I'll go with invisible thing. I don't want to start overthinking about reading people after reading people's minds. So yeah, thank you.
Hi everyone, I am Nishraj. I'm working on embedded and full stack technologies. So my question is like, if you have 25 hours a day, how would you spend your extra time? So obvious answer like sleeping.
Okay. If you could eliminate one food so no one could eat it ever again, what would you destroy? Lemon rice and puliyogre. I hate it. I mean, the reason is I used to have this a lot, and I am very much bored of it now. Yeah, I introduced myself, right? Okay, I'm Omkar, and I've been working here from 5 years, and I work on embedded projects. Yeah.
Hi guys, I am Shyamala Krishna Grawat. I work here in Apra Labs. So my question is, imagine you no longer have to work. How would you spend it usually? I might sleep for a while more, and after that, a web series or audiobook.
So, as you have come just now, so
No, you can keep your stuff here.
this is the ice breaking session. You have to come and pick a chit here, and you have to give an intro about yourself, and there will be a question in it. You have to answer that question. Come.
Suraj Rapa, I'm from Pune. Our startup's name is Totally Creatives. We work on image processing based applications using AI. So, controlling fans and lights using just hand gestures. So, the question is, what did you want to be when you grew up? Like a scientist, I'm working with some chemicals. Yeah.
So that's all for the ice breaking session now. Now we would like to further continue with the main topic and the session. I would like to call up Omkar, Palak and Yashraj to continue.
Okay, so today we are going to cover a lot of things about embedded systems into medical imaging. So we will, we had an introduction. So we will discuss about what healthcare standards are required to develop an embedded project. And we have like 3 solutions for this. One is ARM-based endoscopy solution. Other is a hybrid solution with FPGA and ARM. And the third one is with Nvidia Jetson based solution, which is GPU plus ARM. Then my friend Yashraj will tell you about the Apra Pipes, which is our framework, what we have been developing so far, and we are integrating this framework in multiple fields, like it is in embedded machines, in AI, ML, in surveillance, everywhere we are using this. And it's an open source project, you guys can check it out, try it out, and if you have any improvements, you can implement or you can suggest, and we can work on it together. Okay. So next, code compliance will be taken over by Palak. Code compliance is nothing but like what type of code, how it can be written for the medical imaging industry. So about that she'll be speaking, and then we'll have a Q&A session. Okay. Okay. So this is like, these are the medical devices, the major medical devices which are being used in the current industry, medical imaging industry. You can see it is bulky, endoscope, LASIK, and otoscope. It's like, it's an analog device right now what we have. So what doctors do is they just get into your ears and see in that with their eye like this, like a microscope. Okay, so we are trying to make this like a little bit more compact so that it can have mobility, so that you can take wherever you want. In terms of if there is any emergency or people who can't come into the labs to do these all tests. So next slide. So you can see this has come like very compact. So this is like endoscope which goes inside your foot pipe, which does diagnostics. Otoscope, you have a display directly on the screen, and you have laser. LASIK is like eye surgery what you have, and this is also like quite compact now. Okay, so we were able to achieve this by using some of the chips in the hardware. So you can see this is like Jetson Nano. Jetson Nano is like a credit card size computer now. Okay, same like AMD Xilinx, it's also very small. So we have the world's smallest camera which we are using. So why we are using that is like, it is small and it can be produced many, and the cost will be cheap. So like right now the probes and all what we have, they are like costly and they are not detachable, they are connected. Okay, so with this smallest camera we can have disposable probes, so one time you can use it and you can just throw it away. So that this medical industry, just like syringes, you can use it once and you should throw it away, so that we should not transmit any diseases from one person to other. The same thing we are trying to achieve with this world's smallest camera. Okay, and how can we like say that only this probe can be used once? Because there are people like we Indians or some other, so they try to do jugaad and they try to use the same probe many times. But just like printer cartridges, like you can use it once. So if you try to reuse it, it will not accept. So that's how we are able to achieve it with the authentication chips. So it is embedded inside the probe, and they are very cheap because they are very small in nature. Okay. So let's go to the next slide. So there are some expectations from medical imaging products. So there are some criteria what the standards and medical imaging standards have taken. So it's like the camera preview should not have any, noticeable latency in the sense less than 100 milliseconds. It should be. This was like very nearby. They have decided that it should be around 100 millisecond latency. Otherwise, this was not there before. So next, the frames should not have image tearing. So for example, if you move your probe like this, inside, and if you see some lines coming in, that should not happen. That's called image tearing. So that should not happen. Otherwise, the doctors will think that there is some anomaly inside our body, and they'll treat something else. Okay. So the power isolation is like during the treatment when there is surge, current surge, or maybe anything like fluctuation, that should not cause a shock or anything to the patient as well as to the doctor. So that should be taken care by the power isolation itself. So next thing is the live preview. What we show, it should be lossless. So how you take it from the camera, it should be shown as is. It should be lossless, so that they'll get a very clear picture. In compression, you'll see some of the quality gets degraded, or maybe some lines will come in between, pixelated lines or something. So that should not happen. And the procedure what we are going to do, it will be recorded for future purpose, by the medical practitioners. So those videos or images should not be stored inside the medical device. It should be stored in an external storage, and that access should be only with patients, and only patients can give consent whether that should be used for the future purpose or not. So that's one thing. The device, the embedded device should not be accessible to the outside world, so that there is a chance that, how much ever security you make, there is a chance that hackers can get into and get your data, which is like very much personal to you guys. So that should not happen. So while the this one procedure is going on, the device, if it gets stuck, it should not be like in a stuck state. So it should be rebooted at that instance itself, or there should be some warning or some message should be shown, and the procedure should be stopped then and there with that warning. So that we have to take care of. And of course, Michael Barr is the one who has come up with some standards. So code compliance, like this is how the code should be written. So he has taken care of removing small issues which occurs, repeated issues which occurs, or the code readability which should be proper. So that those are things he has taken care and he has made a code compliance. Okay. So next. So next we will be discussing on the ARM-based solution we were able to make for endoscopy. So like a bulky device which can make it small. So this will be like a single monitor will be there and a board will be attached behind, and a probe can be just added in the side. So in this solution we have like three important aspects, like live camera which should be shown on the screen. Second, during the procedure we have to record how the procedure is going on, that is for video live record, and in the same machine we can just review whatever the procedure was done. Okay, So in live camera, I mean, in the ARM-based solution, we are using Hummingbird. Hummingbird was like 8 years back. It was a very good board, and it was like at that time I think Raspberry Pi and all were there, and Hummingbird was little bit cheaper and which had GPU. GPU in the sense a very small GPU which can take over some of the ISP related operations. So we chose that Hummingbird and we came up with this solution where the camera input was giving us JPEG as input, and we used to decode those JPEG frames, and we used to show on the live screen. We'll show this in a demo how this works. And the same thing in video record, the same source, we used to take it and we used to record into a MP4 container. And we had given an option that you can take a snap also while this procedure is going on. Okay. And the media review is nothing but whatever the recorded content is there, you can view it in the machine itself, the same machine itself. So there we will read it from the USB device, and we have made sure that only those files will be read which we had recorded, not the other files, because USB tends to have lot of files. Like you can store movies, you can store personal videos and all, but those won't come into this. So that type of thing we had already taken care of it. So that reader used to scan the whole device, find out whichever the recorded content is, video, image, and you can review it. And when you are playing this content, you can even rotate, zoom, everything you can do. Because practitioner tends to do all the procedures and all, but they don't tend to know that the camera is whether rotated in proper angle or not. So those things they can take care from in the review screen itself. Yeah. So next we can show the stack. Yeah. So we chose Western Linux as an OS for this. Why? It's because before we used to use Debian Linux, and we saw there was image tearing in that, and there was no way we can fix it because the buffers what it had, it was using the CPU buffers, and it was, the processing was too high, and that ARM processor was like a 32-bit machine, so it was not taking care of correcting that process. This one. So we chose Western Linux so that it does GPU based compositing. And GPU based compositing fixed our issue where the camera was having tearing. Camera frames were having tearing. So that's why we chose Western Linux as our basic layer. Then we used GTK for using UI toolkit. So whatever the graphics we will be looking at, that will be developed using GTK only. So buttons, sliders, keyboards, everything what we have, we use GTK for that. Jansen we use to store some of the configurations. Configurations is like in this medical imaging, wherever you are, wherever you are in the sense like you are inside the body, but sometimes the lighting conditions are not proper. So you have to adjust some of the image parameters like brightness, hue, contrast, gamma, and all those things. And you can save those settings into JSON. So we chose JSON here because it was very small to, it is readable first of all, and it is very small to maintain also. So that's why we are using Jansen to parse those JSON or store the data into a JSON. So during that time we used GStreamer. GStreamer was a very popular tool for getting all the media from camera source to the application, or use it for giving multiple, it used to give like T's. T's are like, right, if a pipe has water and if you want to distribute, you have T, so that you can distribute to multiple sources. So just like that, GStreamer provided this mechanism where you can take it from camera, the frames, and give a T and push forward for rendering or storing into, give it to the encoder or encoder to store into your USB drive. So that's why GStreamer came into picture. And we use FFmpeg for encoding and during playback and decoding. And that's where our application is on top, which will be using all this stuff. Okay, so let's have an endoscopy demo. So you can see this is the end product, what we had developed. That was the end product. And just before this, we had we had this. I mean, you see, this is bulky. Yeah. So you can come. Okay. So you see, this is a bulky solution right now, but this was embedded behind all the circuits we had, and you can easily carry this just a display anywhere you want. So why the mobility was required was like during the emergency for veterinary people. I mean, veterinary pets. For them, if there is an endoscopy needs to be done, they can just carry this instrument. They do the endoscopy over there, and they figure out if what is wrong over there, treat it there itself, or do some emergency aid over there. So that's why this came into picture. So right now this camera is not working because it's been like 5-6 years and it has been obsolete now. This is a single-use camera, and I think we have exhausted those single-use. That's why it doesn't come up right now. Okay. So instead we show the test pattern over here, and this is where the controls are. Where you can do recording. So this is where you do recording from here. Okay. While the recording is going on, you can even do captures. Okay. So I mean, this probe actually goes in, and we have buttons over here. So So basically this probe has these buttons, and the procedure is going on. Doctor doesn't have to touch the screen itself. You can do the recording or image capture from here itself, and if you want to do some rotation and all, you can handle it from here. This here. So there's a camera over here, which is doing the recording, as well as it has some of the LEDs for illuminating inside your body if there's too much darkness inside. Okay. So for that we have used it. You can enter the patient's information using this keyboard. Doctor's information, and that's how it is stored also inside the USB device. And these are some of the settings. These are the presets which, and if there are multiple doctors, they can just use their own presets. Presets are nothing but those are the ISP parameters which you can use depending upon which doctor they are. So these are the parameters what we had. So you can adjust hue, contrast, LED brightness, or this is the ROI, what we can adjust sharpness, gain, and gamma. And this same device we had implemented for medical usage as well as for instrumentation or industrial usage. So this camera has a very good FOV. So you can just, I mean, if you want to see this small characters, you can just focus on this and you can find it out. Okay. We have another demo which, where we can show the pictures and all, which is over here. So this is the improved version. Okay. So I'll just show you that. So this is like an obsolete product right now. The problem was with this product, it had 200 milliseconds of latency. 200 milliseconds is too much. So we improved this architecture. Okay. So I'll just present another slide. So this is totally ARM-based solution. The whatever I have shown you. Unfortunately, I am not able to show you the camera because that probe also is not available right now. I mean, they have discarded that solution itself. But it was working like for 3-4 years. Then we came up with a better solution, which was FPGA plus ARM. So this solution was like FPGA was taking all the heavy lifting in the sense making sure that the camera which we are capturing, it has done all the ISP related operations over there, in the FPGA itself, and the end latency will be 60 milliseconds. That's a huge success over there. Okay, so but this solution had an Austin rendering implementation. So because this is a FPGA based solution, the HDMI, I mean display adapter, is not directly connected to the Linux. It is coming through the FPGA. So we came up with a solution where we did off-screen rendering. Off-screen rendering is nothing but from ARM we were doing all the controls. Controls in the sense LED controls, or start a recording, or do all the changes. I mean, for users, they have to change the ISP parameters and all those things. The whole thing was done by ARM, but FPGA was doing all the heavy lifting, which was rendering, capturing from the camera, do all the ISP operations. This FPGA was taking care of. Okay. So in this architecture, you can see there are two displays. So we have display which is 1280-800, which will be used by nurse, and there is a surgeon display which is 1920-1080. So this solution was developed for LASIK surgery. Okay. So what surgeon does is he doesn't control anything, because he will be focused on doing the operation. Okay. And eye is very small, right? You can't directly see over there. So that's why you need a very large display, and whatever you are capturing should be very clear, and nothing should be like on that display also. If doctor wants, he can see whatever things like settings and all are there. He can see. If he doesn't want that, he doesn't want to get disturbed by that, we can turn it off also. Okay, those things we had taken care of. So here off-screen rendering is nothing but Linux, which is running, which is a Meyer Linux, but headless. You might know the Dockers and all, right? So that doesn't have any display. It is just a Linux command line it runs. So we use headless Linux over here, and we started using virtual frame buffers. So here also we are using GTK toolkit, but those GTK toolkits were creating the overlays in the virtual frame buffers, and ARM was taking that frames and pushing into the FPGA so that it can render. Okay, so it can render in the sense how an FPGA can render these controls as well as camera. So it used to do alpha blending in the FPGA itself, camera as well as overlay, and this alpha blending used to, it used to look like there is nothing wrong with the display, everything is fine, and even the touch screen was not coming through the OS. So we had handwritten our custom touch filter. So it's like wherever you touch, that widget will get highlighted or it gets operated. That way we had done it. So that's where the off-screen, touch screen comes from USB. So this is where we take care of it. Also in this we have LED implementation. So LED illumination was two ways you can control. One way is manually you can ask nurse, okay, increase the brightness for this much percentage or something. That nurse can take it and doctor can do it. Or there was one more where our auto LED algorithm comes into picture, where scene in the sense camera, where it is pointing at. So it will detect what the environment is, and it will automatically adjust the LED based on the scene environment. Okay, so this made better, not having additional job for nurse to adjust the brightness, or doctor to tell and get doctor giving nurse instructions and get disturbed during the procedure. So that we avoided with this. Okay. So in this LASIK surgery, doctor uses obviously a laser, and we had given a doctor a foot switch. That's a Bluetooth based receiver, so that receiver it can be kept in the foot, and he can just control whether to fire laser, whether to rotate that picture or not. So these all things will be was controlled by a foot switch receiver. Okay. So next, I can tell you more about this Zynq. Zynq is nothing but it's a chip from Xilinx. So the FPGA, Xilinx is known for FPGAs. So they made a chip, and they did such a way that FPGA you can design whatever you want, and you can have ARM also embedded in that FPGA, which can be controlled totally. Okay. So inside Zynq, what is there? I can just let you know. Next slide. Okay. So inside Zynq, we have two partitions, you can say. This partition is ARM, and this partition is for logical processing, which is like ISP and all. So our arm, what it was doing is like controlling laser. It was getting inputs from foot switch controller, and based on that, send laser commands. Send laser commands to provide an intensity, like how much the intensity of laser should go, and treat that eye. So for that foot switch we had used probe controller. So probe controller was like, as I said, the probes what we have, those are single use only. So we made sure we using 80 SHA. 80 SHA is a chip, authenticator chip we used, so that the user who is going to use that probe, it will make sure that it will be only used once, and all the information what is needed, it's inside that chip itself in the probe. Okay, and nobody can program it. They made sure that the programming will be done only once. It can burn only once. Okay, so this is, with this we were able to achieve this single use authentication. So as I said, like overlay generator, GTK used to create those control images, and it used to send it to the FPGA, so that FPGA can fuse it, and we can show preview as well as the controls. Okay, so we have LED adjustment. As I said, it has two options, manual and auto. As I said, that can be chosen by processing system. So these all things are the ones which ARM used to do by itself. Control is over the ARM, but FPGA has all the IS related functions which it can do it much faster rather than using ARM do it. Okay, so we'll have a demo after this. Oh sorry, I can tell you about the stack what we used. Oh, pipelines. Sorry. Yeah, pipelines. So here the pipeline was like the overlay was generated by the ARM, the FPGA buffers, and we used to send all those overlays controls into FPGA, as well as FPGA used to mux this camera source and the overlay generated stuff and provide it into a touchscreen display, as well as it used to provide on a this one, another display which is not touchscreen, but it is only for the doctor's use. Okay, so this controls like feedback from users, we used to take it from touch filter, and that's where overlay again it is to generate, and using that feedback, and a different overlay will be generated, and again it will be merged. Okay, so the video recording pipeline is almost same as what we used in the last project, but here the camera, camera source is controlled by FPGA, which is programmable logic. It is to take all the camera buffers, keep it into the FPGA buffers, and there was one signal which used to tell us that there is a new frame available. There is a new frame available. We used to go there, take that frame, encode it, and store it in the USB device. That's how we used to do it. So the communication mechanism between ARM and FPGA was AXI register. So just like you have I2C for controlling all the devices, peripherals, or you have GPIOs to turn on, turn off, or UART to send some serial communication. But this is internal to the, FPGA and ARM are internal to them. So how the communication will happen was through AXI registers or AXI bus, you can say. So these registers were like 16-bit registers, and we used to send some information, and FPGA used to sample it every 60 FPS. That what is the next control, what we have to do, or what we have to overlay, those all things. So next slide. Yeah. So I was talking about this 80 SHA authentication a while ago. So it's like when a probe is connected, at that instance we check with 80 SHA chip what is the serial number. Next, if we are able to get serial number, we'll proceed. Otherwise, we'll say, okay, you guys are not valid. Okay. Next, we used to do authentication. 80 SHA authentication is like they have some APIs where you can get the challenge with private key. You give back the answer. If it is authentic, it will give you a response. If it is not, it will say it's failed. It's a failure. If the authentication succeeds, what happens is we increment the it automatically increments the probe count internally, 80 SHA. And if the probe count gets incremented, that's like you have used it for once. And after that, whenever there's another probe connected, if the same probe is connected back, then we'll see if the count is exceeding one count, then we don't even consider that probe. We don't even show the camera frames on the display. So that's like a probe is useless now. Okay. So this is how we had done it. Next. So the software stack is like, as I said, we are using a Xilinx chip that is nothing but CZU3EG. That's a SOM. It's an ultra scale SOM. It is quite expensive compared to the ARM solution, but it does the job. I mean, it gives you less less latency. We have laser module, foot switch for treatment. We are using a OmniVision smallest sensor. So I wanted to show you that. So this is the smallest sensor which we used. This is like 1 mm. It's a 1 mm sensor. It's a size of a grain, actually, rice grain. Okay, you can see this and pass on. It's inside this sleeve. Just be careful.
This OFCs.
Those are not OFCs. Those are wires, electronic wires, but they are like hairline wires. That's why the sleeve is added so that the soldering doesn't come off. If it comes off, we are not able to find it.
Is it also single use?
Yeah, that will be a single use because it is small in nature. So it will come in, I mean, if you do a bulk order, it will come in very less price, and you can just throw it off once it is used.
Why is it single use?
Sorry?
Why is it single use?
Single use is like you do all the procedures and all, right? You don't have to use the same probe for another.
Oh.
So just like syringes you have, you don't reuse it. You don't transfer the diseases with this. So that is the smallest camera till now we have, and it has a very good FOV also. If you see, like it's not like microscope, but it can see very minute things inside your skin also. You can see dirt. If you clean also, there will be a little bit of dirt remaining over your hands, and you can see that also. Okay. Okay, so that's the smallest camera we used, and with that camera we can have LEDs also around, and which can illuminate the scene, and that's how the auto control LED will, our algorithm will work, and it will make sure that the whole scene is nice and doctor doesn't have to do anything other than doing procedures. Doctor has to do it. Okay, those procedures. So next thing what we can do is, I told in the previous slides the GTK, Jensen and FMPEG why we had used it. So the new thing what we have here is Termios. We use it for UART communication. UART is like single wire communication what we have, serial. And high Redis is a library we use Redis internally, so that some of the application states we can keep, like there is an onboarding process, just like you have in Windows. When you boot up for the first time, you have to fill your your credentials or set up OneDrive and all those things. So just like that, we have some onboardings over here, which can be, those states and all we maintain in Redis. So Redis is like a storage device inside this one. So for that we used high Redis. Yeah. And the communication medium here is I2C, GPIO, UART and Axibus. Axibus is for communication between ARM and FPGA. So Palak will show you a demo, like the solution what we have made. So this is how the end product will look. Okay, and this is like currently in FDA now. It is going through FDA. Once this is approved, then it will be used for everyone.
So this is the insides of this machine, and this is the nurse screen where the nurse will operate and how the proceeding should go on. There's a doctor screen that.
Yeah, we will just change.
Yeah, we'll show you. This is doctor screen. So what happens is, this is the foot switch where you can, where the doctor presses to fire the laser and it's connected to the probe. Probe has both camera, this is the camera, and laser. Since we cannot use laser for reality, so we are using laser simulator over here. This is the camera. As you can see, the camera.
You can see the small particles.
That's not that's why. That's because of cold. That's why I said, yeah. So that's so yeah.
We are not judging you.
So it's that clear and
Very
it
high
has,
voltage standard.
yeah. So this is the camera which we have. There's a different kinds of modes. You have to turn on the laser to press the foot switch. When you press the foot switch, you can see it goes to orange. That means it's streaking. At that moment, the laser is being fired. Laser power right now is 0.05 and duration to 0.05 seconds. So for that duration only, laser will be fired and then it will not be fired anymore. You can increase the duration. You can increase the aiming density, like how much should be the aiming beam should be, and then you can fire it. We have recording. You can record the procedure. As you can see, recording has been started. You can record the procedure, and we do not store the recording directly in the system. We store it in the USB device. Then only you can. If there's no USB device, you cannot record anything, and it will not even show. We have different kinds of peripherals where we show if their system is available or not. Green shows it's available, and if I remove it, it will show green. Like suppose if I remove USB right now, it will show red because I have removed the USB while the recording was going on. There are different kinds of notifications which shows what has happened and like that. And while suppose the procedure is being going on, and if somehow the power cut or some problem, there's an emergency switch. When the emergency key is being pressed, you can see the laser has been stopped. It's not in ready state anymore, and you cannot use the laser, as you can see, right as of now. This is the foot switch, and
So these are just toggle buttons for our development thing. But initially, how it will happen is whenever they are using probes, right? They'll just release their hand, and the procedure will be stopped. That way it is. But here for development, we are using these switches.
yeah.
Yeah.
So since as Omkar has mentioned that this doctor uses foot switch to operate the operation, and he is in leg. So when he presses the foot switch, the laser is being fired. He can change the camera orientation like that. And if you want to see, we have two kinds of rotation in this. One is the diagonal rotation. Then we have a superfine rotation where it goes slowly towards where you want it to.
Yeah. And you can change the rotation also.
Yeah, you can change, like right now it's set to 90 degree, 45 degree. You can change it to anything. If you see, we have different kinds of settings where you can change whether to show indicator or not. We have mask where the circle goes into square goes into circle, like that. We have different kinds of settings for the operation. Then if the doctor says that he doesn't want anything else in the screen, he just wants the procedure. He just wants to see the procedure and then nothing else in the screen. You can remove everything else from the screen. You can only see the camera over here, and if he changes any of the peripherals, this will come up, and after 10 seconds it will go away.
Okay. So as you know, doctors are very much into the procedure and they don't want to get disturbed by anything. So that's why we have this. And if you don't want to have this settings appear also, we have that setting that you can completely turn off. Even if nurse changes anything, the settings won't appear. Okay. The only thing is this emergency errors and all, it will be shown over here when the procedure is going on.
Because that is important.
Yeah, that is very important.
What's the FPS of this camera? Smart.
Right now it is at 60 milliseconds latency, and it is running at 60 FPS. Yeah. Thank you for that. Okay, so this mask, I mean, you know why this mask is getting used is, you might be having this question. It's because when you are rotating a picture which is like square, you can see all the edges coming in. It's getting chopped off. Some of the frames are getting chopped off. So even that gets somehow disturbed. I mean, by a surgeon. So that's why we have a mask. What it does is it can just see the picture and you don't have those rough edges shown on this one. Okay. So this solution is quite expensive, but compared to the ARM-based solution, very expensive, like $350 one saw it will cost. Okay. So we came up with okay, let's change this. So next, what we did was, in order to reduce this cost, I mean, obviously, wherever the cost is increased, you have better chances. I mean, you can have you can extend your ISP to have much more stuff which can be done and all. But we came up with a cheaper solution which can do the same thing whatever we are doing right now. We don't know what the future is, but right now whatever things are there, so that can be accommodated using Jetson devices, Nvidia Jetson devices. So all the heavy lifting which was done by FPGA, now those things can be done on GPU itself, because GPU is quite faster than the normal ARM ALU operations. So by taking this advantage of GPU, we were able to achieve the same latency at 60 frames per second over here. Okay, so in Jetson Nano, we have GPU, we have ARM, and as I said, Apra Pipes is the one framework what we have been developing from past 3 years. So we are using Apra Pipes to, take advantage of GPU as well as ARM. Okay, all the pipelines, like taking it from the source, I have sources like camera over here, taking it through a CSI lane, processing, give ISP operations over there, and having overlays or rotation, pan drill zoom, whatever is there, it will totally handled by the Apra Pipes through GPU. And this is the I think first time we are using in the medical field, and we are able to make it nice. We are able to achieve the same thing what we were able to achieve on this one FPGA based solution. Okay, but this has opened the doors for AI and ML also using Jetson Nano. Jetson Nano is the cheapest SOM what we have from Nvidia. It's like $100. On $100 you'll get one this one Jetson Nano. But it has opened doors for AI and ML, which can find out anomalies inside the body. It can detect that the anomaly is, which will make easier for the surgeon to identify. Instead of he searching everywhere, the AI will just highlight this is where things are. So that's why we came up with Jetson Nano approach, and Apra Pipes supports all types of source, transformation, and sync. So it can be anything. Here source can be anything like camera, it can be text, audio, anything. Okay, as long as it needs some transformation. So Apra Pipes will handle it. And we are using the same AT-SHA chip over here for probe authentication. Okay, and we also have these two different displays for surgeon as well as for nurse. We have we are using the OmniVision's hardware ISP, which supports usage of multiple camera resolution, so that we don't have to do much like hardware change in Jetson, so that we can support different camera probes over there. So if doctor wants to see 400 or 720p or 12, 1920, 1080p resolution camera frames, the OmniVision ISP supports. Okay, so that's like a single point of contact for the probes. Okay, so in LED right now what you have seen, it's a PWM based driver what we have used for intensity. But in some cases you don't require a PWM for a high range of LED to be shown inside. You don't have to have a very bright environment inside, like very bright LED inside. So for that we are using low current drivers, and we have an option for high current drivers also. So high current driver mostly gets used in instrumentation industry. Okay, so that's where we are using it. So overall it's same as what we have done it for FPGA, But here it's not off-screen rendering, it's on-screen rendering. On-screen rendering is nothing but a touch display or HDMI adapter is directly connected to the arm, and the transition of overlays and all is very smooth with this approach. So here it's like a win-win situation with a cheaper price. Let's go to the next one. Okay, so in this architecture, what we have done is like we are using a open box or LXT Linux. You can use any, and you can have same performance. Like there's no image tearing, nothing is over here, and we were able to achieve this. And we use the same Jetson GTK for rendering or configuration, and here for GPU pipelines, I mean ISP pipelines, we started using CUDA. CUDA is like they give you APIs so that you can control. I mean you can design your own ISP operations and all over there. So we used CUDA, and using Apra Pipes it was possible to do this. Okay, so we have Apra GTK utils. It's like I mean for GTK what we have, I mean those are the very low level APIs. So we over the years we found out like these are the repeated code we are using, or I mean whatever the solutions we have made we are using. So we started using our own framework as Apra GTK utils, where we can use it in any of the product like medical, surveillance, anywhere, and where you can get the UI feel, I mean UI toolkit feel. With this you can do it. And Apra utils is like in order to do, as per say GPI or UART or low level communications between the peripherals, we started using Apra utils. That's also a homegrown product for us right now. And obviously we have our application which is running. So next thing. So this is just a comparison I wanted to show you guys. So the first solution what I have shown you, it has a 200 milliseconds latency, which is not acceptable at all. So over the recent years, they have, and medical standards have done it, like only 100 milliseconds, 100 to 150 milliseconds latency should be there, or below is fine. Okay. But that was a low cost solution also. But this solution can be used still in industrial because then we don't have frame latency at all. We can still use this solution. Next, the FPGA ARM-based solution is like we had two solutions for this. So one required a high amount of ISP operations or needs to be done where a bigger FPGA was needed, which was ultra scale. Okay, so that ultra scale FPGA was a $350, which you saw a demo. That was a $350 solution. Okay, but they have a lower variant also, which has ARM 32-bit processor, and you can use FPGA also over there. But it has the same latency, but you can't do much of ISP operations over there. So that is restricted because of that. So it's a medium solution. So if you want to go for a cheaper solution with a good latency, we have a Jetson-based solution, which is GPU plus ARM, where latency is also 60 milliseconds and the cost is also low, $100. Okay. So that's all from my end. So Yashraj will take over and he will tell you about Apra Pipes, how it works. He can give you some overviews, insights. Okay. Thank you.
You told about the laser product, but what about the endoscope, which is Garner, FDA or something?
I mean, that's what we had developed a product. So they said like, because it took like around 1 year to develop that product, and it came out. But later the surgeons and all, they said there is too much of latency over here. Then they revised the whole medical imaging standards, and they said like it should be 100 to 150 milliseconds. Now this product is there for instrumentation, but for medical imaging, I mean for endoscopy, we have Jetson-based product. So
it's under approval?
Yes, it's under development. It will be soon, like next month or so. It will be going under FDA approval. So this is the one what he's going to talk about. Yashraj is going to talk about.
So hello everyone, I am Yashraj. I am just going to tell you the insight of Apra Pipes, why we are using it, and like how it's been helping us. So Apra Pipes is our in-house pipeline framework for developing video, image, and audio sourcing application. You can also have AI/ML on it. You can just make a inference on it. So this is the repo. I'll also show you that link. You can just fork that repo. You can just try running some tests just to get an idea like how it works. Also, like if you want to contribute, you can just add your own modules, and like if you want to ask something, then you can just raise some discussion on our discussion page, and we'll help you out. So why we are using it? Because this is the best practice, like whatever we have learned for past 15 years. So whatever industries use like PNG, Streamer or FFmpeg, whatever is the key concept and like whatever makes them better, like we have just inspired from them, and like we have developed our in-house framework. It's easy to use. You just need to define like what all modules you will require in your application. Suppose I'm writing an application which require a camera, so then I have a camera source. Then I just need to define a pipeline like how one module will be connected to this. So suppose my use case is that I want to scale an image, so I'll have a camera source. I'll add a scale after it. So it's just a plug and play module. You just need to do set mixes. You don't need to write actual codes. It's highly customizable. So suppose if you just take a simple example of rotate or scale. So I want the scale factor to be 2.5. I want the image to be zoomed. So just instead of going into the code and doing changes, we can just define the properties, like what all properties are there. So for rotate and all, there will be angle. For scale, there will be scale factor. So just like this, all modules have their own properties. You can customize this and like you can use however you want. This Apra Pipes provide this cross-platform support. You can build Apra Pipes on your ARM device or on your Windows or Ubuntu or Mac OS, anywhere. We also support multiple frameworks like OpenCV, NPPI. NPPI is Nvidia's API, FFmpeg, GStreamer. And the other good thing about Apra Pipes is like if you want to integrate any new framework, then it's like super easy. You just need to define like how the module should look and what all APIs you want to use, and you can directly use it. So just like any other pipeline, we have these three basic modules. First one is that source. Source is the guy who will produce frames. It can be a camera source, or it can be a file reader, or it can be an MP4 reader. This module is responsible for generating frames. This is the transform, like whatever frame you are getting, what you want to do on top of that. So as I said, like if you want to do a scale, then you can do a scale. If you want to do a rotate, then that also you can do. So suppose also if you want to do some color correction, or if you want to make some adjustment on ISP level, like hue, saturation, contrast, all those things can be easily done using transform modules. So whatever transformation you have done, at the end you want to either write it, or you want to see it like how whatever you have done is like right or wrong, or like is correct or not. Then you can use a Zynq module. Zynq module is basically can be anything. It can be a render where like you will see how the frame is looking. It can be a writer where whatever frames you have written, you can write into a file or into a MP4 container, and it will generate MP4 for you. Also, you can use these frames to transmit using some RTSP Zynq module that can be used as a RTSP or somewhere. So this is the basics about Apra Pipes. I'll just walk you into the core concepts, like how like we have defined and like what all things is required. These are the key terms. So as I said, each module is an independent. Like source is an independent module, transform is an independent module, Zynq is an independent module. Source will run on its own thread, transform will run on its own thread. Same goes with Zynq. There can be a multiple source module, there can be a multiple transform module, there can be a multi-process module. It's totally dependent on you, like how you want to use it and how like what your application requires. So it's totally on you. So any modules are connected with each other using this pin. For source, there will be only an output pin because there will be no input to it. For Zynq, there will be only input pin, there will be no output pin. And for transform, there will be some input and it also generates some output. So each frame comes with this metadata. Metadata is some basic information what the frame contains. It will be either width, height, or like what will be the property, or image type, whether it's RGB image or a mono image or anything, also YU image. So that thing will be a part of metadata. It will just define like how your frame is. Suppose, for example, if in case of audio, it will just define you that wavelength or bit sample rate amount. The next is frame. Frame will actually hold your all the information related to like how's your image looks. It's just the frame buffer. Frame container is a set of frames which will hold multiple frame on it. So as I said, like each module is running on their separate thread. So whatever the source will produce, it will transfer it to the queue of next module. And whenever this transform module will get any frames in this queue, it will just take that frame, it will process it, and it will just transfer that queue into that next into the next module. So this Zynq will take that Zynq will take that frame, and whatever it want to do, suppose it want to render, then it will render. If it want to write, then it will write. So when you will just do this, link this model from source to Zynq, this is called a pipeline, and just like any other pipeline like GStreamer or FFmpeg, this is a simple, the same concept what we are using. So here are some examples of source, transform and Zynq. Right now we have around 80 to 90 modules which are there. I have listed some basic out of it. So these are some example of source module. A source module can be a camera, it can be a file reader, it can be a MP4 reader, and there is also a possibility of omniverse data generator. So if you have knowing about this omniverse data generator, this is used for generating virtual data. And then there is one network source, like if your data is coming, if your input is coming from some RDSP URL, then you can use this network source. The transform also can be anything. It can be a rotate, scale, resize, or it can be used for image or text only. Also, you can have a lot of RSP filters like hue, saturation, contrast, black level, and so on. If you want to infer, like everyone is using machine learning nowadays, so we also have a support for model inferencing. You will just give an input, and whatever inference it will generate, it can generate an inference. So we also have this encoders and decoders, which is written in both, which is written for CPU, which is written for GPU and ARM. We use Nvidia as well as Intel's API for that. Also OpenCV. So based on your requirement, you can use those transform modules. Zynq can be a renderer where you just want to render whatever you are getting. It can be a video writer where you will generate a MP4 container. It can be a stat sync just to see like how your pipeline is performing. It can be a file writer just to save frames and all. And like network sync can also be one other where you can just give this as an RDSP sync as an output. So this is a pipeline that we are using to develop that application. This is similar to that endoscope one. So here our input is, and it's a camera source. So it's very easy to connect any of it. So it's a camera source which is going to this transform module. Transform module is doing nothing, it's just converting this YUV image type to a YUV344. Why we are converting it to YUV344? Because we don't want to lose any data, and as we are doing everything for medical thing, and it's not possible for us to lose any small kind of data also. So that's why we are converting it to YUV344. Then we have this rotate, scale, and translate. This is so suppose if someone just rotate, then what we need to do. So for that we are using this rotate, scale, and translate module. So we have an independent module for that, which is called as a file transform. Then again we are connecting a mask model. So suppose if you say I want a circular mask or octagonal mask, you can have that using this mask module. Whatever you have generated till now, we want to see it like how it's looking. So we have a render at the end, and these are the two other keys. One is for writing a MP4 file. So when suppose if you are doing a surgery and you want to record a particular operation, you will say start recording. Whenever you will say start recording, this valve will open and it will start getting frames. whatever frames we'll get, we'll encode it, and then we'll write it to M4. The other key is going to this save frame. So while doing an operation, you can also save frames. So that time also we'll open this wall. So we'll only open the wall for once because you will save capture for one. And whatever frames you have got, you will save it to the disk or into your system. Next is the demo. So, so it's the same thing. Whatever you have saw there or like whatever you see. It's just that upgradation of these devices. Just it's cheaper and like more. It's a like latency is like little less. Like latency is around 16 milliseconds, and there the latency is around 100 milliseconds. Now also this is a cheap solution. So that's like there is. So this is very. Yeah. This is a probe. Just see the same camera like it's combination camera. You can just plug out this probe. Like if you are basically a part of probe, you can just plug out it and just plug it.
So because this is in development, the removal and hiding of probe is not there. But that is like almost quite a furnished product. So it will be same as like that. Okay, LEDs will be on top of this, and camera will be over here. Same. You asked me right about the endoscopy because this higher latency. This is the lower latency solution for them.
So this is the place where you can save frames, and also whatever you have captured you can save also. So this is our review page where whatever you have captured or whatever you have recorded you can play it. This is the video which we have recorded on that you can do it. Also like if you want to record a new, then you just need to do a start record. Yeah, the field of view is pretty good.
So it depends, like because you can have multiple cameras over here. So for medical imaging, you can't use wide angle because you need the minor information which is very close to the camera. Here the focus will be not that much, but over there you can see like minor stuff. So that's why we are given an option. You can have multiple cameras over here. You can use wide angle or whatever resolution you want, whatever it is. So that's where the OmniVision's ISP comes into picture. That you can use any type of camera. Still, this solution works for medical as well as industry. So that's the one which goes inside your eye. So it has to be very small. Okay. I mean, most of the people what they have tried is using what is it, optical fiber to do it. But it tends to happen that it breaks up or some distortion will occur, and because of that you won't be able to capture the frames. I mean, very nicely. Here the camera itself is on the tip wherever it is going. So you have a very good chance of having the picture very nice, crisp, and you can see very detailed.
How are the probes practically? Seeing like this or something different? Whenever it is entering the volume.
Yeah.
Is it same or something different?
It will be furnished kind of.
That's it.
Yes. That is for endoscopy because like in your food pipe, if you put a very small probe, it can wander around. Okay. That's why it has to be, I mean, the size can differ depending on the food pipes. Okay. So you have many, pipes. You will have many options. But what they try to do is, in food pipe, when they put, it should not wander around inside. They try to keep the camera stable. That's why they keep it such a way that it should be compatible with your food pipe. And you can see the view. But in the front of this, it can wander around like this. That way. It can do the check.
Right now, if you want to actually close the simulator for LEDs and all that, then like it will be a finding like this. So this like you can actually control to our LED. So you will see that. So parts is like we're using GPI. If I just change the if I just connect the jumper on it, then it will use low current, or it will use a high current. Then it's using low current cables. So this is definitely like whatever we have recorded in past, all those media will be shown here. Like it will be a Nvidia, image file, all those things will be part of it. Also we have this user settings thing. So suppose if you want to change date or you want to move to some other preset, each preset it will have their own settings. So suppose whatever settings you used in the last operation you want to switch it back, then using those settings. This is the advanced settings thing. So same here, like even from here also you can switch between those presets. If you want to adjust the hue, AGC or saturation, then using this slider you can adjust all those things. Saturation, contrast, AGC. Also like there are a lot of there are like different kind of cables that we are using. For that we have different profiles for different. There is an auto or manual mode for each. Like there are some range for mouse. You can go from 1 to 6 based on your requirement and based on the lighting condition. You can apply those, and then at the end you can see.
And here the cable length also matters, because each cable length will have some distortion, and that can be corrected with precise. So that's why we have different profiles for each cable length, as well as some profiles for each of the doctor, or the same doctor can have multiple profiles if he wants to do something. And you saw that mask, right? Round mask for doctor. Some doctors prefer round masks, some doctors prefer diamond masks, which are like cut edges. Isn't that?
So based on your requirement, or you can opt any of it. So want to go for that. So like majorly like then just uses this circular mask instead of square or and also
yeah. One is for endoscopy we had. So I told you about there is a cheaper solution in FPGA plus ARM, right? So that we had used for otoscopy for years. Yeah, with a higher latency. Unfortunately, we don't have that setup because that project was over and we had given back the hardware. Okay. But the way was like a band was set to the patient, and there was a very small display which was mounted over here, so that doctor can do his operation. He can see it in that display. And the controls were also less but small. Yes.
USP of this is low latency and small size.
Yes, small size. Correct. Correct. And here, main thing is these probes are single use, so you can use it and throw it. Okay. So other things are like you have to use that probe, which are very costly actually.
So when you say single use, is the only reason because we are not used for other patients?
Exactly. So I mean, those probes can be used by other patients, but there is a lot of maintenance. You have to sanitize it. You have to boil. Those stuff needs to be taken care of, and we are avoiding that.
So when we are not using those probes for other things, we are just throwing it to garbage. We are
It will be
recycling.
used for recycling. It will be recycled because you know, right? In doctor's clinic, you have 3 different bins. So there will be another bin for this. Okay, and this will be like widely available later. I mean, if anyone can purchase this from any store, kind of thing. Just like syringes now, you can buy from anywhere. Okay, you can just carry it from
Cost of the probe
$5 to $10.
The only camera.
Yeah, it will be cheap because it is very small and it can be produced in mass. And it will be very cheap. Right now it is expensive, but when it is produced in mass, it will be dead cheap. The same with authenticator chip also. Right now the authenticator, that authenticator chip is costing $0.5, which is like 50 cents. Very cheap. So as a complete solution, it will be more cheap. I mean, the prediction is $5 to $10. It can be much cheaper than that.
You see that it's like super, whatever you do, during flight also, whatever you do, that will directly see. So in medical settings is the main you want, you can't like have a like a reason.
So here the Apra pipes what we are using, it has like very less latency, one frame latency you can say. One frame latency. One frame is like 33 milliseconds. If it is a 30 FPS camera. If it's a 60 FPS camera, lesser than that. This is a 30 FPS camera, what we are saying.
Like why we are able to achieve it is because of that zero copy operation throughout the whole pipeline and not copying one buffer from another. Just using that same buffer, whatever we want to use, whatever we want to do with that buffer, and not copying it to some other place.
Very heavy in the sense like
high processing power or
yeah, because the image, I mean ISP operation, now if you want live like latency and it has to be so fast and you have to process so fast that it has to have good power, good amount of power. Right? And I mean this is not so hot if you just touch it. And it's not using like 100% of CPU or GPU over here.
Hardly uses 30% of the
Yeah.
so there is no frame loss frame.
No.
like not even less than 1% or
There is no frame loss itself because we have one frame latency and there is no queue itself. I mean you have queue of 3, in that only maybe 1 or 2 gets filled, not more than that. So there is no way it can lose any data. And in medical devices, frame drop is not an option. Prices, this is a $100 chip, Jetson Apra.
And entire setup with cameras.
With mass production, it will be cheaper, I think. I don't know the exact cost because this is like not our product basically. This is for startup. Yeah. Yeah.
100,000. So
Not
10,000.
No, it is less. Not that much. It's a $100 chip making the board maybe like $300.
Under 100.
Yeah, under. Less than 1 second.
With camera.
Yeah.
So completely dedicated to you or you are collaborating with you?
No, this is totally done by us. I mean, first we used to, our client used to provide us the hardware and we used to do it. This is the first product where we have developed our hardware. We have developed the software also. Because see, we have this, right, a barrier where someone develops a software and hardware and we are developing software. Too much of barrier, asking questions, getting debugging done from that. It was taking too much time. So now we have an embedded division where hardware is designed here, software is also designed here. If there's any question, queries and all, it gets sorted out here. And that's why we are able to develop this product, I mean, around 2 or 3 months. The whole thing, with manufacturing the device, getting the software, all those things, done on this organization itself. The only client will do is he has to pay and take this product. And he has to take the FDA approval. Obviously, I mean, the objectives and all will be given by the client, and we have to get out a solution for those objectives. Yeah, so this is the Jetson based. Okay. So next stop, Palak will be taking over on the compliance, code compliance. Yes. Yeah, this transform is running on software but on GPU pipe. NV is Nvidia. We can have QA session after this, and we'll answer all your questions if there are any. Okay. So Palak is taking over for this.
So, code compliance is basically a certain set of rules which are to be followed in a code in the whole system, so in order to avoid any hazardous runtime errors which we may not see, which we may think it's fine, it doesn't matter to normal people, but in medical field especially, even a small mistake can lead to a human life. So there are certain set of rules which we follow. So it was found by a person called Michael Barr. He was the one who made this whole system, and he said that the bar code, it's called bar's embedded coding system and standards, and it aims to the reduce programming defects, and following this you can reduce headers and debugging time and improve the maintainability. This whole system was to maintain a code portability, to reduce redundancy, and make it more appealing, like more readability, because we know that for now we are working on the system, but we may never that maybe our next 2 years or whatever can work on this. Even for them, they should know what is going on, and it should be look readable. It's not like the person will be always working on the system. What are like the common issues which we may not see in day-to-day life while working is mistakes in the project requirements, misunderstanding by for requirements by implementers, oversights in system or software architecture, insufficient handling of hardware failures, inadequate response and exceptional runtime circumstances. So it can be anything apart from that. So these are the common things which we neglect. For instance, there's a nested if statement should not go beyond 2 levels. We go beyond 3, 4, 5, we do not know, but it should not go beyond 2 levels. Then every switch case statement should have break at the end of the case. Sometimes it doesn't matter, like there will be cases where if we do not add break, it will not matter, but it does. If we don't add break, it will go through each and every line of the code, and it will increase the time complexity. Then function should have only one exit point. That means the function should have only one return and not multiple return statements. The length of the program should not go beyond 100 lines. Like in a function, it should not go beyond 100 lines. Then the braces, use proper braces at the proper place and give the good white spaces to make it look good. Then proper abbreviation and acronyms. And as we know, when we were college, we used to use int A, B, C, D, X, Y, Z. We cannot use that in here, because if we are using, suppose we are using a variable X, we are doing some operation, we have to go through backtrack each and everything where we have used X and Y it was used for. Instead of that, it's simple, you can use, if you use a name for it, so we'll know that what it was used for, and stuff like that. So avoid use of code, continue, then should not comment any block of code. The file method should have a public header file and with the same name, like the header file and the file name should be the same. Should be the integer, the data types which we use should have in fixed width. Like we use in embedded system, we have to use in 32T, in 64T, or U in 32T. We have to use like that. Then cache value of an update, like there can be a case where we are using a certain function in a function, it's a recursive function, and you're using a certain functions which is taking the value from somewhere in hardware. If we use the whole function to each time take the value in a multiple statement, the value can update, because it's taken from hardware, the value can change. So we should, instead of taking the value directly from the function, we should save the value at the beginning of the function, then use that variable the next time, because it can update anytime in the between while the execution of that function is going on. It can lead to any problem. So now that I've mentioned about the bar standard, can you tell me which one is more towards bar compliance and which one is not?
First one is towards
This one. Why do you think so?
I think if followed those rules which was last time.
I guess it's second time. Because we have break statements
This one is more vast-sided, it was vaster because we have not used break statement over here, we have used break statement. Even though it doesn't matter if you enter the date, but it will, if I don't add break statement, it will go through each and every case. It will increase the time complexity. The time also here and here. If we use this is the, suppose if I had taken the value as minus, it will go here, take this, go here, then go here. It will break and it will out of the system. And if I don't add break, it will go through each and every line, which will increase the time complexity. So yeah, this one is more towards bar compliance. What about these? Anyone can say.
Right. I think right.
Yes, right side is about to go towards bar compliance because we have again multiple return statement and we should not use, our function should not have more than one exit point. It should only have one exit point. I've mentioned that our function should not have multiple if statement. There can be problem where people think that how is it possible to make multiple, how should we avoid multiple nested if statement. So here's an example how we can avoid it. If suppose we are checking for like which one is among the three is the greater number. What we usually do is if it's greater than that, we say that x is greater than y, and if it's greater than then we do it like this. To avoid this, we can do it. We make a function where we compare two variables and say that this is greater than that. And we set the value of x and y. If this is true, then it should, and we add the bool call should continue. If this is true, then it will go to the next. Then if it's true, then we'll say what is the value is. Like that.
So this bar compliance is needed in the medical standards because when it goes for the FDA approval and all, they check the whole thing, code, everything, because they don't want to leave anything, left behind. So whole code review, everything will be happening over there. So that's why we have to follow these standards for medical. So if you have any questions, please ask us. Me, Ashraf, and Balak can answer. And a few of them you have asked before, but still, if you have any questions.
Is there any testing parameters that you do before sending it to FDA, like whatever the approval you need?
Yes. So, Yashraj will tell, he uses glass to glass latency check. That is one. Second thing is we are using a tool, static code analysis tool, to find out if the code is bar compliant or not, or if there are any more issues. Issues in the sense which are not related to bar compliance, but in code analysis, if there is a memory leak itself, which is unnoticeable sometimes while developing, or if there is any standard which, MISRA standards is the one where embedded people use it, MISRA. So even that, the code, static code analysis goes through the MISRA bar, everything, and it will give you some results. So that is one thing. And the end of the, unit test is one more thing. Like each model what you develop, you unit test it before it goes to the QA. So that most of the issues you handle it on your end itself. Okay, unit testing is one more thing. This comes under development cycle. QA, they will be having multiple test cases. They go through all those things, and then only we give a release to the customer. And customer also does it through their own stuff. So Yashraj had developed glass-to-glass latency. So glass-to-glass latency is nothing but like
It's a photodiode experiment. So you must have know about photodiodes, right? Yeah. So photodiode is like no receptive towards light. So we place that photodiode on a screen. Okay. Then we just flicker one LED. Okay. And we solve and we check like how much time it actually takes to get that flicker on the screen also. And basically we take the difference between those two timings, and that actually gives us the actual latency whatever. And the other simpler way is to can just have one mobile phone. You can just point it. You can just point your camera toward that, and you can start one stopwatch with milliseconds, and then you can just basically measure the difference, like whatever you're seeing on the screen and whatever you're seeing on the camera. So that will also give you details.
Any more questions?
One last question.
Yeah.
Since you already made it very compact,
Yeah.
in near future, would you make it more? Is there any chance that it would be more smaller? Like,
Sure. I mean, depending upon the requirement, as I said, like if any customer or anyone says, I want this to be displayed on a smaller screen and it should be compact. Yes, we can make it compact. So it will be, obviously there will be some challenges, but we'll overcome it. Yeah. So I told you, right? There was one product where the display was this much, a credit card size display, which we used to get mounted on the head, and people used to, doctors used to perform surgery. Years ago. That is called otoscope actually. Yeah. So that we had made, but with Jetson we have not made because we did not get that requirement. But if that requirement is there, we can do it. Any more questions? Okay. Any more questions from live audience? I don't think so. They can communicate with us.
They can ask questions.
They can ask on the by text.
I don't see any questions.
Okay, then we are good. I think Srishti can take over.
So thank you, Omkar, Yashraj and Palak, for this wonderful session. Thank you to the online and offline audience for your patient hearing. I would now like to call up Akhil to speak a few words.
What do you want me to speak about?
He's our sale.
Yeah, you spoke about company already?
Yeah, I did.
Okay.
But you can speak one more time.
Well, all I can say is thanks for joining and thanks team for all the effort. Our idea of these meetups is to promote deep tech. I mean, if you see in HSR Lab, there are so many companies. Everybody is trying to do something great. We want to be part of that ecosystem and we want everybody else to be part of the ecosystem. So please let your friends know that we have these meetups once every month. So this is the November meetup. I think the next meetup is in January. It will be in ISC campus, ISC Bangalore campus. We are visiting there with a booth, and we are also going to have a 3 or 4 hour long technical session. One of them will be a meetup on one of these advanced tech topics. We also have a YouTube live channel, so you can see past streams. Last one was LLM, right? Yeah, last one was on generative AI and LLM, which is something that we are very actively working on. Are there any questions? Visitors, you have any questions? No. Anybody else? Thank you.
Thank you, Akhil. I would like to request you all to give your valuable feedback. You all can have some snacks.
So there's a fun fact, the packet that you got, there's a pen on the back side of it, you can use it to even use your phone. That's just a very interesting fun fact for you. Please have some snacks and